Hi everyone, this is my presentation for the M4 Final Hackathon. In this project, we solve a binary classification problem predicting whether an individual has prediabetes or diabetes using survey-based and health-related features. The target variable is diabetes binary, where 0 indicates no diabetes and 1 indicates prediabetes or diabetes. Because this is a medical risk prediction task, the objective is not just high accuracy, but reliable identification of positive cases, where false negatives are especially costly. I began with the exploratory data analysis. I first checked for missing values and duplicate observations. The dataset is relatively clean, but I removed exact duplicates to avoid bias and potential data leakage. Next, I examined the class distribution, which shows a clear imbalance with positive class as a minority. This confirms that accuracy alone would be misleading, so metrics such as recall, F1 score, and RC, AUC are more appropriate. I also analyzed the correlation matrix. While some features are moderately correlated, there is no severe multicollinearity that requires aggressive feature removal. In addition, I applied principal component analysis for diagnostic and visualization purposes. PCA shows partial separability between the two classes, but the boundary is clear non-linear, which motivates the use of tree-based and ensemble models rather than purely linear classifiers. For modeling, I followed a progressive strategy. I started with logistic regression using L2, L1, and elastic net regularization. These models provide a strong and interpretable baseline while controlling overfitting. To adjust class imbalance, I systematically compared multiple approaches. The standard models on imbalanced data, class-weighted logistic regression, SMOTE-based oversampling, and balanced ensemble methods. This comparison allowed us to evaluate how different imbalance handling techniques affect recall and IOC-AUC, rather than relying on accuracy. I then moved to ensemble models, including random forests, extra trees, balanced random forests, and histogram-based gradient boosting. These models capture nonlinear interactions between health indicators and consistently outperform linear baselines. I also implemented a neural network with feature standardization, L2 regularization, and early stopping. While the MLP performs competitively, tree-based ensembles remain more stable and easier to calibrate for probability-based evaluation. For model evaluation, I did not rely on accuracy. I computed confusion matrices for all models, explicitly reporting true positives, false positives, true negatives, and false negatives. Importantly, I introduced a cost-sensitive evaluation framework, where false negatives are penalized more heavily than false positives. Based on the cost function, I tuned the classification threshold instead of defaulting to 0.5. This is especially crucial in healthcare applications, but missing a positive case can have serious consequences. Models were ranked using a validation leaderboard, primarily based on ROC-AUC, with F1 score as a secondary metric. The best performing model achieved a high ROC-AUC while substantially improving recall for the positive class, making it suitable for medical risk screening. For interpretability, I applied permutation feature importance on the validation set. The most influential features include variables such as age, BMI, and indicators related to cardiovascular and metabolic health, which aligns well with established medical knowledge about diabetes risks. This consistency between model behavior and domain understanding increases trust in the model's predictions. Finally, I submitted probability predictions to Kaggle, since RCAC is threshold independent and aligns with the competition metric. In summary, this project demonstrates a complete and medically informed machine learning pipeline, including data clean and exploratory analysis, robust handling of class imbalance, regularized and ensemble modeling, cost-sensitive evaluation and threshold tuning, and model interpretability. Thank you for watching.